All right. Uh, Over the last two classes, we have studied the working of gas dynamic lasers, where we have basically focused on as to how the thermal energy stored in a gaseous mixture can be maneuvered to create population inversion and in turn lasing. Today, we focus our attention on the working of fiber lasers. Before we do that, let me very quickly once again summarize the principle of working of a gas dynamic laser. For this, we take the case of a gas dynamic carbon dioxide laser. The three modes of vibration of carbon dioxide molecule that we know are symmetric mode of vibration, bending mode of vibration, and asymmetric mode of vibration. This is the ground vibrational state, which can be represented as 0, 0, 0. That is, all the three modes are in the ground state. There is no excitation in any of the modes. So this is symmetric mode of vibration. These are the first excited state of symmetric mode. This is the second excited state. This is the third excited state. And so on. So this we call symmetric vibration ladder. We can call it ladder because the step size is same. This being vibrational energy levels. Then you have the bending mode. So this is the first excited bending 0. This can be represented 0, 0, 0, 0, 1, 0. Sorry, this is 0, 2, 0. This is 0, 2, 0, 0, 3, 0, 0, 4, 0. What is important to note here is that the one quantum of excitation, the energy required, the quantum of energy required to excite one quantum of excitation of bending mode is about half of that required to excite one quantum of excitation of the symmetric mode. This comes, as we see, quite handy in the operation of gas dynamic carbon dioxide laser. So this is the 0, 3, 0. This is 0, 4, 0, and so on. So this is the bending vibrational ladder. Then we have the asymmetric vibrational ladder. This is the first asymmetric excited vibrational energy state. This is the second asymmetric excited vibrational level. This is third, and so on. So this is asymmetric vibrational ladder. So the quantum of energy required to excite one asymmetric mode of vibration is the highest, while the energy required to excite one mode of bending vibration is the least, while symmetric vibration excitation lies in between. Now, when the gas temperature is very low, then most of the carbon dioxide molecule will reside in the ground state. This is well known. Now, as the temperature is elevated, the gas is made hotter. The molecules from the ground level keeps going up to the higher vibrational energy states in all these modes of vibrations. Of course, by satisfying the Boltzmann thermal distribution law for that given temperature to which the gas has been heated to. Now, in this operation, we know that once the gas has been, temperature has been elevated, following that, the gas is rapidly cooled by subjecting it to undergo expansion through a nozzle. And as the expanding gas cools, the population residing at different vibrational levels of each mode of vibration can relax within itself through resonant vibrational collision transfer. Resonant vibrational energy transfer through collision. This process of energy relaxation, vibrational energy relaxation is extremely fast because the energy stays at vibrational energy only. The form of energy doesn't change. For example, let us assume that this molecule, carbon dioxide molecule, at 200 level, that is CO2, 200, it collides with a CO2 molecule at the ground state, that is CO2 000. So this molecule then can come down to this state. So as it comes down here, as it appears here, its vibrational energy, this energy is released because the molecule has dropped down from here to here by colliding with a carbon dioxide molecule in the ground state. Therefore, this vibrational energy is readily absorbed by this molecule and it climbs up here. This is possible because this energy and this energy is same. So it is resonant vibrational energy transfer. The energy which it releases, this molecule absorbs it. And because the energy doesn't change form, such collisions are absolutely efficient. And all the molecules residing at higher vibrational levels through such vibrational resonant transfer collisions will eventually drop down and get accumulated in this level. Why in this level? Why it cannot go easily further down, that is appear here? That is because a molecule here, if it has to drop down to this ground state, then the vibrational energy that it would release, it has to be transferred as translational energy. That is, it must appear as kinetic energy of this molecule. And because the form of energy changes from vibrational to translational, such processes are much slower compared to this VV resonant energy transfer collisions. So for this, the CO2 molecule in 100 state, if it has to collide with a CO2 molecule in the ground state and come down to the ground state, then the energy that is released, vibrational energy, it has to be realized as translational energy. Translational energy that basically would be the kinetic energy of this ground state. So such processes are extremely slow. However, the same thing would happen for the energy which is stored in the vibrational ladder. The molecules which have climbed up to the higher vibrational levels, bending modes levels, they would also collide within itself, and the energy is relaxed and eventually comes down here. Now, because the bending mode energy of excitation of one bending mode is just half of that of the is nearly half of that of the symmetric mode. Therefore, another vibrational energy relaxation occurs here, where the CO2 in symmetric, first excited symmetric mode of vibration would collide with CO2 ground state, and this molecule can actually drop down to this level, and the vibrational energy it releases, the ground state carbon dioxide molecule absorbs this energy and goes up to this state. So basically, it results in two CO2 molecules, the first excited bending vibrational mode. So then this actually provides a nice coupling between the symmetric vibrational ladder and bending vibrational. And once the molecule has come here, the relaxation process from this to the ground state, as I said, would be again a slow process, because the energy is now transferred from vibrational to translational form. However, this process becomes even slower there when the amount of quantity of vibrational energy involved is more. So what happens in the case of asymmetric mode? So once again, the molecule here will collide with a molecule in the ground state, and it will come down here, and eventually all the molecule will get accumulated here. So once this is, this is the upper laser level, and these are the lower, this is lower laser level, and 0 to 0 is also another lower laser for the operation of CO2 level. You already know this. So now, once the molecules have come here, if it has to come down to the ground state, it will be again a VT relaxation. This much energy has to be transferred as translational energy. And because the energy, vibrational energy that has to be transferred as translational energy is much more compared to this, therefore, this relaxation is even slower, much slower compared to the relaxation process from 010 to 000. Therefore, as a new equilibrium takes place, as you have cooled the gas, there is a possibility that at some point the population of this level can become more than either this or this. That means it establishes a population inversion, and lasing can occur both between this transition and this. This will give rise to 10.6 micron band, and this will give rise to 9.6 micron. Now, if you add nitrogen to this gas mixture along with CO2, if you add nitrogen, and if you raise the temperature, then the nitrogen higher vibrational levels also would be populated. And as you know, nitrogens, this is V equal to 1, V equal to, this is nitrogen, V equal to 3, and so on. Now, because the close matching of the vibrational excited state of nitrogen with the asymmetric mode of vibration of carbon dioxide molecule, therefore, if a nitrogen molecule and the nitrogen molecules which will climb up to different excited states, it will also collide among themselves, the excited molecules and the ground state molecules, and eventually the energy will be relaxed and nitrogen molecule will come down to this state. Once again, the relaxation from here to here is again a very slow process. However, if nitrogen molecule in this first vibrational excited state collides with the carbon dioxide molecule in the ground state, then this energy which will be relaxed, this vibrational energy can be absorbed by the carbon dioxide molecule in the ground state, and it will climb up to the first asymmetric vibrational, excited vibrational state, because this energy and this energy is same. So then this will lead to the excitation of carbon dioxide molecule in the first asymmetric mode of vibration, plus nitrogen will come down to its ground state. This is nitrogen ground state, which is V equal to 0. So that way you will enhance the population inversion. If you add helium with this mixture, then helium has is an efficient additive which can remove this vibrational energy through VT relaxation. That means helium plus CO2 and 010 will result in bringing the CO2 down to ground state, and helium will have the transition. However, helium cannot remove this vibrational energy as efficiently as this, simply because the vibrational energy involved here is much more than this. Therefore, you see the addition of nitrogen and helium also makes the operation of the laser, gas dynamics laser, more efficient. Just in the same way, it actually helps the operation of the conventional carbon dioxide. So I hope you have understood the underlying physics of the operation of a gas dynamic CO2 laser. Basically, how the thermal energy that can be stored in the among the various vibrational levels by elevating the temperature of the gaseous mixture can be maneuvered to establish population inversion between the two energy levels and in turn achieve lasing. All right, with this, let us turn our attention to the working of fiber laser. You see, one of the performance parameter of a laser is undoubtedly its power generation capability. The performance parameter of a laser is often judged by its ability to the generation of power. And it is not surprising that continuous effort has been expended to push up the power output from a laser ever since its invention in 1960. However, as we know, there always exists a challenge in increasing the output power. So why? Because you know that a fraction of the pump power is always dissipated as heat in the active medium. For example, let us consider a operation of a laser based on the 4-level energy configuration. So this is the ground level. So this is the pump level. This is the upper laser level, and this is the lower level. So in the beginning, this is the source or the ground level. Source or the ground level, where to begin with all the species, all the molecules reside in this level. Now let us assume that we pump one of the molecule up here to the pump. It then will quickly relax to this, and this is where the lasing transition takes place. So suppose the lasing transition is at wavelength lambda, and suppose we optically pump it. Just consider it is optically pumped. So the pumped photon has a wavelength, so lambda p. Of course, lambda L will be more than lambda p, because this energy is less than this. Now see, to generate one photon, you have spent an energy which is more than what the photon is actually has. So this difference of energy, that means this minus this, which is essentially this much energy, is stays back into the system, and it is eventually is dissipated as heat. So if you try to increase the output power of the laser, that means you will dissipate more power into the system. So that will increase the temperature of the blazing medium. And unless you have a mechanism to remove that heat, it will increase the temperature, and as a result, the population of the lower laser level will increase. This will tend to reduce the population inversion, and in turn will have an adverse effect on the performance of the laser. Therefore, removal of this heat is actually a challenging task, especially for solid state laser, as they are characterized by rather small surface to volume ratio. Why surface to volume ratio is important? Because you see, a solid state laser, as you know, is normally is in the form of a cylindrical rod, that is the host into which the light emitting atoms are doped. You know that. So usually it is in the form of a solid rod, is the host. Now, in this, you have actually doped your light emitting atoms. Now, as a result of lasing, the fraction of the input power that stays back into the system, it heats up this medium. So the heat which is generated inside this rod, it has to diffuse and arrive at the surface, from where it can directly dissipate out into the air, or this heat can be removed by the help of coolant that can be flown around this surface, and the heat will be removed. So more is the surface area, better, more is the area of this surface, the heat can be removed more efficiently. So for a better heat removal, you would like to have a surface area, a volume ratio should be more. If this is more, then heat removal efficiency is also more. Efficiency is more if surface area to volume ratio is more. So with increasing power, the laser rod invariably suffers from the effect of thermal lensing that grievously affect the spatial quality of the output beam. If you cannot remove the heat effectively, then as we have seen that it actually results in thermal lensing effect, which greatly affects the spatial quality of the output beam. And further, if this is the center of the rod would tend to become hotter than the edges, and that actually creates a expansion, uneven expansion. The center would tend to get expanded more compared to the edges, because the center temperature is more. That will again generate a mechanical stress which can actually damage the rod. And if you try to create more output power from the laser by dumping more input power, then this effect will be further enhanced. That's why it is not easy to extract more power from a laser simply by putting more input power. Thus, with increasing power, the laser rod invariably suffers from the effect of thermal lensing, and also mechanical stress also can be generated that can even damage the rod. Now, in a gaseous or liquid laser, thermal management is less difficult, as the waste heat can be dissipated simply by flowing the hot fluid through a heat exchanger. You can actually use a pump, say for a gaseous or liquid laser. You can actually make use of a circulating pump. You actually use a pump and a heat exchanger. So this hot gas or liquid, hot fluid can be, this is heat exchanger, this is a recirculatory pump. So the hot gas will flow through the heat exchanger and it will give out its heat to the heat exchanger, and cold gas will enter. So that way you can actually manage, the thermal management may be much better, and the active medium remains cold all the time, which is not possible for a solid state laser. So that is the major problem of increasing power from in the operation of a conventional solid state laser. So then here comes the fiber. The only exception of solid state laser that is free from such drawback is a fiber laser, which makes use of a gain medium similar to that of solid state laser but varies widely in geometric shape. The active medium of a solid state laser is often a light emitting atom doped glass rod, typically several centimeters in diameter and tens of centimeters in length, and it has low surface area to volume ratio that you have already seen, that its surface area is less. Lasing in a fiber laser also originates from a similarly doped glass, but in the form of a fine strand, several micrometer to millimeter in diameter and several meter to even up to many kilometers long. The thin and long geometry readily offers a remarkably high surface to volume ratio, and thus the fiber laser have inbuilt capability of rapid dissipation of heat to the surroundings. Well, I end the today's class here, and next class we will see why or how fiber laser makes such a big difference as far as heat dissipation is concerned, and why it is capable of producing much higher power which cannot be produced by a solid state laser. The principle of operation, that is of both these lasers are same. In both these there is a host which is in solid state glass rod, and in a fiber laser it is a strand of glass, and in both of them you dope the light emitting terms. Same also true for a fiber laser, but it provides the advantage of producing much higher power than what is possible from a conventional solid state lasers. All right, so let me end my lecture today.